Okay, so today we're just going to be reviewing the Chapter 16 practice problems from Solomon from our class materials. So let's start with number 1. What is the correct Iupac name for the following compound? So for ketones, that O-N-E is going to be your suffix. It comes at the end. It's not a free prefix, so it's going to end in "-one", whatever it is. And then I count up the parent chain. So 1, 2, 3, 4, 5, 6, 7, 8. So the parent chain is 8. So whatever else, it's going to be octane, but we're going to obviously at the end have octone instead once we combine it all. And then I find my substituents. So the ketone is at carbon 4. If we numbered it the other way, it would be 1, 2, 3, 4, 5. But because it's the highest priority, we want it to be lower. So 4 is better than 5. So we're going to go with 5. Or with 4, I mean. So it's 4 for the one, and then at 7 we have a methyl. So then you just combine it all. So in this case, you're going to say 7 methyl, 4 octanone. So what else you could do, if you're trying to be more specific, you can say 7 methyl octa, I think it's octan 4 one would be the right one for that. So that just puts the 4 right before the suffix so that you know exactly what it's talking about. It's just a little bit more specific. Both of these are correct. Iupac is moving towards this one lately, but either one of these are right. So I don't want you to get confused on the MCAT or whatever if that comes up. So the right answer for this one would be answer choice B. And then for number 2, the correct for the following compound would be which of those below. So this is an aldehyde, and aldehydes end in Al from aldehyde. So that's an easy way to remember it. So whatever it is, it's going to end in Al. 1, 2, 3, 4, 5, 6 is the parent chain, so that's hexane. And then substituents are a 2 and a 5 dimethyl. So then you can combine it all. It'll be 2, 5 dimethyl hexanal. So I didn't put 1 in front of the Al because unless there's something higher priority than aldehyde, it's always going to be carbon 1. And the reason it's always going to be carbon 1 is it has to be at the end because of that H there. If it was in the middle, it'd be a ketone. So you don't usually specify where the hexane is unless for some reason it's paired with a higher priority item. That doesn't usually come up. So the right answer should be answer choice B, 2, 5 dimethyl hexanal. What's wrong with this one is the numbering system is wrong. This is just a made up something. Might be a common name, but it's not Iupac. And then heptanone, that's 7, so that's why that one's wrong. And hydro is not something that we use, so that would be wrong. Okay, number 3, 3-phenyl propanol. So I would just draw this out. Propanol means prop is propane, so there's 3 carbons, 1, 2, 3, and there's going to be an aldehyde on one of them. So you've got your propanol right here, 1, 2, 3, and on carbon 3 is a phenyl group. So it looks like that. Immediately, even if you can't draw that, if you're not sure, you can get rid of this, and this based on the fact that they're not aldehydes. They're ketones. So if it ends in Al, it's got to be an aldehyde. So that narrows it down automatically to 3 and 5. And between 3 and 5, or 2, I don't know why I said 3, 2 and 5. And between 2 and 5, 2 doesn't have enough carbons. It only has 2 carbons. So that can't be right. That'd be 2-phenyl ethanol. So answer choice E is your right answer. So you can narrow it down to a 50-50 shot just if you know what the Al means. So be looking for those things when you take your exams. Also remember, sometimes you could have benzyl, and benzyl has a bend in it. So it would look like that before the parent chain. So just be aware of that. Benzyl and phenyl are 2 different things. LAH cannot be used to convert carboxylics into corresponding aldehydes because, okay, LAH is a really, really good reducing agent. So LAH is going to take a carboxylic acid, and it's going to first eliminate this oxygen right here. So it would have an intermediate that was an aldehyde, but then it's going to eliminate one of these bonds. I guess it would eliminate both of these bonds to this oxygen. So it would finish with, no, it would be one of these bonds to this oxygen. So it'd finish with this. So it goes from a carboxylic acid to an aldehyde to a primary alcohol. This is a hydrogen right here. So because it goes to a primary alcohol, first you eliminate this bond to oxygen, then you eliminate this bond to oxygen. You can't eliminate the last bond to oxygen, but it'll go very quickly. This is even easier to reduce than this. So because of that, it's not going to stop at the aldehyde. This is going to be very fast intermediate. It barely forms before it's being reduced even further. So it's going to go all the way to the alcohol. So the right answer is whichever one says that. Not sufficiently active is not right. It's so reactive it goes too far. Converted to this structure would just be, it's basically deprotonated. So just a base would do that. Any base that's going to take off the proton. Reduced to the primary alcohol, reduced to, this would be if it could get rid of that last alcohol. It can't, just the way reducing agents work. And then converted to this would basically turn it into a ketone, which we haven't learned how to do that from a carboxylic acid right now. So that's not right either. So that leaves you with answer choice C. Okay, identify the reagent that would be capable of bringing about the following reaction. So let's just go over, I think this will just be helpful. The ease of reduction series. Let me look at my notes real quick. I always mix up the first two. So the easiest thing to reduce is a ketone or an aldehyde. Because the aldehyde is the easiest thing to reduce, that's why you don't see carboxylic acid stop at the aldehyde. It's even easier to reduce. And this R could be an R group or an H group. So NaBH4 will reduce these down to a primary alcohol or primary secondary alcohol. LAH will reduce all of these down as far as it can go to primary or secondary alcohol. If you want to stop at the aldehyde, you need a weak reducing agent. And so I wasn't a part of it, scientists created what I like to call LAH's cousin. It's lithium aluminum triterbutoxy hydride or something along those lines. I always get that a little mixed up. But what that does is it can make you stop at the aldehyde version. So it would reduce this is a minus, so it'd be Cl or whatever. It can reduce that to the aldehyde and then stop. So that's what LAH's cousin is designed for, the lithium aluminum triterbutoxy hydride. That's what it's designed for, is to get to the aldehyde and then stop. So the only thing that would take you from this, oh, that shouldn't be an O there, it's just the Cl, to this would be C. NaBH4 would reduce all the way down to an alcohol. I guess that would be a primary alcohol. And LAH would go all the way down. But this is specially designed to take acyl chlorides to the aldehyde. So it's going to stop at the aldehyde phase. So if you ever see an acyl chloride being reduced down to an aldehyde, it's that. The other thing you're going to see a lot is esters being reduced down to an aldehyde, and you use diol H usually for that. So those are two special things that are made specifically to get aldehyde, special reducing agents made specifically for an aldehyde. Because it's so hard to get an aldehyde from up here. It's so easily reduced that anything that's going to reduce a carboxylic acid is going to reduce an aldehyde as well. So if you start with a carboxylic acid and you want an aldehyde, you first could convert it to an acyl chloride with SOCl2, PCl5, something like that. And then you can use this reagent to get an aldehyde. because otherwise, like we just talked about in the last question, that wouldn't work. Okay. Question 6. Dissolving benzaldehyde in methyl alcohol establishes an equilibrium with what compound? This is basically just a reaction question. So this is benzaldehyde. You should have learned this in chapter 14 with methyl alcohol. And we've learned this, I think we talked about it already in chapter 12, but anytime you have a nucleophile with a carbonyl carbon and it's not an acid base, it's going to attack at the carbonyl carbon and kick this up. So you'd get an O minus, that's a minus, not a methyl, your H, this oxygen, and this CH3. This actually has only one lone pair there, and that should be a positive charge. Then through equilibrium, your proton will be transferred up, so you could draw the arrow around like that in order to reach an equilibrium, and you'd get this structure. We've talked about that a lot. This nucleophile will attack, it'll kick this up. If there's a good leaving group, it'll come back down and kick it out. There's not a good leaving group because it's just a hydrogen. So instead, it'll form an equilibrium with this. There are a few other ones on here. I don't know which answer choice that is. Let's see. I think that's answer choice A. So for answer choice A, got the OH here, the hydrogen. Yeah, answer choice A. For answer choice B, the problem is that to get this structure, you'd have to have kicked out your existing hydrogen. And hydrogen's not a good leaving group. So this isn't going to come back down and kick the hydrogen out to get this. So that can't work. To get answer choice C, C is actually just kind of crazy. It looks like this. OCH3, OCH3, OCH3. I don't even know how you'd get that with this structure, so that wouldn't work. It looks like answer choice D is an equilibrium between the right answer, but also this answer choice B, which wouldn't work, so that wouldn't be right. And then E is a combination between answer choice B and answer choice C. So we know those wouldn't work. So the only right answer is going to be answer A. Okay, this is a fun one. Number 7. I think you guys are going to like it. Villager or Villager, Bayer Villager is usually what I call it, is just using MCPBA, which you guys have usually seen to turn double bonds. MCPBA or any peroxy acid, you usually see it to turn it into epoxides, right? That's what you're used to seeing. But what this does is just insert an oxygen to one side or the other of a ketone. That's all it does. It turns a ketone into an ester. The trick is you need to know the migratory aptitude. The migratory aptitude, the first one I believe is hydrogen, but I don't want to tell you wrong, so let me refer back to my notes. Number 7. Okay. Yeah, hydrogen will move over the most easily, then phenyl, then a tertiary alkyl group, then a secondary alkyl, then a primary, then a methyl. Okay, so what this means is whichever side has this group is going to move more easily. So up here, you have a secondary or a tertiary. So the tertiary is ahead on the list, so the oxygen is going to insert itself right there. You're not going to get rid of any carbons. It's just going to put itself in the middle there. So you'll have your oxygen. Then you still have your methyl group. It helps to number, I think. I'm going to go around the opposite way. So we have 1, 2, 3, 4. I have terrible ability to draw. 5, 6. What are these called? Heptagons? I'm not very good at them. Usually I have to do one of these. And then you can put the oxygen right there, and there's your methyl group. So something like that. But I'm not good at drawing them on the fly. That way it looks crazy. Okay, so I'm sorry. Let's see. 1, 2, 3, 4, 5, 6. So that's right here. So it still has all 6 carbons on it. And it just has the oxygen right here inserted. So the right one for this is going to be answer choice C. This one's wrong because it's not even inserting the oxygen. This one's wrong because it replaced a carbon with the oxygen. This one's wrong because it inserted it on the wrong side. And this one's wrong because it replaced a carbon with oxygen and inserted on the wrong side. So that's Bayer-Villager. Let's look at another. I think the next few problems are also Bayer-Villager. Yes, okay, so a peroxy acid with H and an alkyl group. So it's H, then phenyl, then primary, secondary, or tertiary, secondary, primary, and then methyl. So we've got an H on one side, so the oxygen is going to go right in there. That's much easier to draw, so you're literally just going to look for this. And the right answer for that is answer choice A. B inserts it on the wrong side. It's the wrong migratory aptitude. This inserts it on both sides. That's not going to happen. This gets rid of a hydrogen altogether, so that's a mystery, and this is just crazy. So that's not going to be right. So these are pretty quick and easy once you get the hang of them. And 9, let's see, we've got H, phenyl, tertiary, secondary, primary. So on this side, it's tertiary, and this side is primary. So this side is going to go first, so you're just going to insert an oxygen right in there. So it's going to look like oxygen and then this on the other side. So this one, it inserts it on the wrong side. This answer choice B looks like the right answer. This inserts it on this side and turns the other side into a carboxylic acid, so that's not right. And this does the crazy double ketone thing, which is not something we've even talked about, so that's not going to be right. So your right answer is answer choice B. Okay, and then, question 10. I love these kinds of questions, these multi-step ones. So first, KMNO4 does 3 things. First, anytime you have, with a few exceptions, an R group off of a benzene ring, it will convert it to a carboxylic acid. So it becomes benzoic acid. The second thing that KMNO4 does is it will cleave your double bond to do a ketone. If one of these is a hydrogen, it will actually convert it, because it's a strong reducing agent, it will take it all the way to a carboxylic acid. If that's hot KMNO4. Cold KMNO4 will add an alcohol to either side of your double bond. And that's pretty much it. That's what KMNO4 does for you. So the first step here is this. It's going to turn this, KMNO4 is going to turn your benzene into a carboxylic acid. Then you use SOCl2, so that's X. You use SOCl2 to turn it into a chlorine. And then you're going to use lithium aluminum triterbutoxyhydride to, we talked about this in an earlier question, convert it to an aldehyde. So you go from a chlorine to an aldehyde. So the right answer is just going to be answer choice E. This one's wrong because, well, it doesn't even get you your chlorine, so that's not right. Oh, I was wrong. Your right answer is actually answer choice C. This is a carboxylic acid, not a aldehyde. Whoops, sorry, my bad. I was just looking for that hydrogen. Okay, this is wrong because it's an ester, so that's not going to happen. And this just stops at a weird spot, skips over the chlorine, so that's not right. So you're just looking for the benzaldehyde. Okay, this next question, and that by the way is a good test-taking technique. So I do tend to just jump for what looks like the right answer, but I do make myself go back and look at everything else and tell myself why I got it wrong. Because that one will check to make sure, did I get everything that I am trying to get right? Like, did I miss anything? Is there an answer that's more than one of these or something like that? And then 2, when you're studying, that helps you think through, are there any other concepts here that I'm forgetting? So that's just helpful. Okay, this question, the reason I conveniently put your KMNO4 stuff off to the side, is hot KMNO4. So it's going to cleave right down the middle. This is what would happen with cold KMNO4, so that's not right. This cleaves but doesn't add the oxygens in. So when it cleaves down the middle, you're going to, I just imagine it inserting, sorry, I kind of have to go off to the edge there. I just imagine it inserting an oxygen on each side of that right there. So you get 2 of this structure, which happen to be the same structure, but it doesn't always have to be that way. So that would be answer choice E. 3 has the cleave but doesn't have the oxygen inserted. This should look like that. It just adds an extra hydrogen. And this one cleaved one bond but not the other, so it's not right. So your answer is answer choice E. Okay, diol H. We talked about diol H. So what diol H does, we talked about it briefly, is it takes an ester and it converts an ester into an aldehyde, and on this other side, it basically just cleaves right there and adds a hydrogen on each side. So it's an aldehyde, and the remaining ester becomes an alcohol. So in this case, the ester is a ring, but it's going to do the same thing. It's going to cleave down the middle. It's going to add a hydrogen and a hydrogen. This isn't obviously the official mechanism. If you want to learn the mechanism, that's fine. I don't think you're going to be tested over it, so it's just easier for me to think about it like this. So we're going to end up with an aldehyde and then a ring with OH and a methyl group down at the bottom. So that 1, 2, 3, 4, 5, that means we have a chain that has 1, 2, 3, 4, 5 carbons, and on the 5th one it has an alcohol. So the ring is broken, so neither of those are right. So that takes us down to C, D, or E. D makes this other oxygen into a ketone. That's not right. So then we're down to these 2. Well, this one doesn't turn it into an aldehyde. It turns it into a carboxylic acid. So that's not right. So it's only going to be answer choice C. Just in case, let's check how many carbons it has. Oh, that looks right. 5 carbons with a methyl group and an OH on the last one. Methyl group and an OH. So that's right. Okay, let's go to number 13. 13 is a review of the last chapter. So AlCl3 with a benzene ring and an acyl chloride. That should say ding, 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 Friedel-Crafts acylation. So I'm going to flip this upside down because it's easier for me to visualize when it's on this carbon for whatever reason. So we have 1, 2, 3, 1, 2, 3 with a methyl. Okay. So that's what we're going to get from the first step. This is I plus MCPVA. You should remember what that is. We just went over it. It's the Baeyer-Villiger oxidation. So H and then phenyl. I spelled phenyl, all kinds of wrong. Phenyl. Then tertiary, secondary, primary, and methyl. In this case, you've got a phenyl on one side, so that will be the side where the oxygen is introduced. So oxygen, and then your carbonyl group, and then this side is unaffected. So that's what we're looking for. This answer choice is actually just I. It's what's right here. It's funny because that's what they labeled it as. So they didn't use the MCPVA step. This answer looks right to me. This has it inserted on the wrong side, and this turned the benzene into an epoxide, which wouldn't happen because benzene rings don't act like regular old double bonds. Okay, for number 14, this is actually very similar, except first, you're going to convert your carboxylic acid to acyl chloride. Then you're going to do a reaction. Same thing, we've got an acyl chloride, Lewis acid, and a benzene. This is a Friedel-Crafts acylation. But in this one, we have an electron donating group present. So just to review from last chapter, when you have an electrodonating group, it's going to go ortho or para due to those resonance structures. And that's going to be on your chapter 15 exam, so be sure that you know that. Usually I just pick one to carry out the reaction and know that it could be on either side. So I'm going to do para just because it's further away, so I like that. So this is going to direct your Friedel-Crafts acylation to a para position. So It'll look something like that. We've got 1, 2, 3 carbons, 1, 2, 3. I always check just to make sure. And then the next step is an addition of a dithiol. So this is the first step to a Raney nickel reaction. Okay, there's no hydrogen there. So when you add any ethane diol or ethane thiol, it's going to attach to the carbonyl carbon. Knowing the mechanism for this is worthwhile, but not absolutely imperative. So basically what happens is it attacks the carbonyl carbon, kicks up, and forms a bond here, and then the other side does it again. This oxygen gets protonated twice from these two alcohols to make it a good leaving group, and it leaves, makes it water because it gets 2 protons, and then you have this new structure. The same thing can happen if those oxygens are sulfurs instead. They act very similarly. So the sulfur attacks, kicks this up, it'll get protonated from that hydrogen. The other sulfur attacks, kicks the other one up as it's protonated from the water. So from the hydrogen to become water. So that's the basics of the mechanism. I don't think you really need to know it. If you remember, I mean, it's always better to know the mechanism than to memorize, but if you have a thiol that reacts with the ketone, it's going to form this structure, and then you can use Raney nickel to just delete it. Boom, just like your Clemmensen or your Wolff-Kishner reduction, it just deletes it and turns this into an alkyl chain. Easy as pie. Because it's ortho-para-directing, either of these would probably be a possibility for your answer. So that's what I'm looking for, either the ortho or para addition of 1, 2, 3 propane. And that's useful because you could not attach propane with a Friedel-Crafts alkylation because it would undergo rearrangement. So that's a good way to know how to primarily attach alkyl chains. So this one stops at the addition, stops at B, basically, that's B. So that's why that's not right. This one adds meta, so that's not going to be right because it's ortho or para directing. This is one of our possible answer choices based on down here. This is all kinds of crazy. The chlorine's left over. Sorry about my email. The chlorine's left over. I don't know what's happening. Let's ignore that. And this one also is all kinds of crazy. I don't even know how you'd get that structure. So answer choice C is your right answer. Okay, 15. So HCN, the CN is going to attack and kick up. This will probably actually get protonated first, leaving CN minus, so that would be OH plus. That kicks up and attacks, and you end up with CN on one side and OH on the other. Then lithium aluminum hydride plus acid is going to reduce your CN. So the way I think of this is it starts out as carbon triple bond nitrogen. Basically what happens is it breaks 2 of these triple bonds and adds a hydrogen for each one on both sides. So when you reduce a nitrile, you end up with, and you have your alcohol over here, something that looks like this. It takes a nitrile to an amine. And sometimes it's hard for students to see how does CN turn into NH2. Well, it's CH2, NH2, and that's how it just fills in those hydrogens there. So basically, you're looking for an amine and an alcohol. So this one is the first step, but it doesn't undergo the reaction with LAH, so it stops after the first step. This one is all kinds of crazy. It's a CN, but then it does an elimination reaction, which would need an acid to protonate it and a base, so I don't know where that comes in. This one looks right. This one's even crazier. I don't know how the alcohol moves one step out, so we'll ignore that. And then this is if you didn't know properly how to reduce the CN, you might guess this is what it reduced to. So answer choice C is your right answer. Okay, question 16. This is a Wittig reaction. So with Wittig reactions, first you have to create what's known as a yelid, and then you do the box mechanism, okay? So that's how you do a Wittig reaction. That sounds confusing, but I'm just going to lay it out for you real quick. C6, CH2Br with this phosphorus thing is going to react. The phosphorus has an extra lone pair, so it's going to attack and kick this out, just like you've seen before in a substitution reaction. So then you end up with this phosphorus. Oh, wait. It's right here. So this is your carbon. This is your carbon, and the phosphorus takes the place of bromine. Sorry, this is just a mistake. So you have 2 hydrogens here, and then I just shorten it to 3 R groups because it does not matter what's on this phosphorus. You could just call it spaghetti for all I care. It doesn't matter. And the formal charge on phosphorus, because it's lost an electron because it's sharing one, basically, is positive. Phosphorus starts with 5 valence electrons, minus 1, 2, 3, 4, no lone pairs, equals plus 1. We're not used to seeing things with 4 bonds be plus 1, but phosphorus isn't carbon. It's in a different category. Okay, so after you have this, a weird thing happens, and that's a base will come and take this hydrogen away and make a double bond right here. And that neutralizes the phosphorus, and it makes this carbons fine with that double bond there. But it can also exist in a form that's known as a yllid. So a yllid is when there's an anion and a carbocation. So basically this lone pair goes up here, and then you have a positive charge over there. These are resonance structures of the same thing. This is called the yllid. For the purposes of this reaction, you make a yllid, and then you'll see what happens next. But what I'm going to do is take this yllid and react with it because it's easier for me to visualize like this. So this is what we have. Our yllid in the double bond form, and then I'm going to line it up with a reaction. So the first step, these two reacted like an SN2 to make this, and then we had the base come and take that proton to make this, and now we're adding this to it. So that's the step we're on. Okay, so I always line up the carbon-oxygen double bond, and you'll see why, like this. And then, let's see, there's a CH3 on this side, and there's a benzene ring on the other side. Okay, so what happens is, this attacks here, and this attacks here, and it makes what's known as a box. Obvious box. The phosphorus makes up one corner. This carbon right here makes up the other corner. It has an H off that, don't forget, and then it has a benzene ring on the other side. Then down here, this carbon makes up another corner. It has a methyl group and another benzene ring. And then over here is an oxygen. So this attacks and forms a new bond right here. This attacks and forms a new bond right here. Each of these double bonds goes away. Then it happens again. And a double bond is formed on this side, and a double bond is formed on this side, and the top and bottom bonds of your box are gone. So it still has the same things as it did before. Now this is your phosphorus and oxygen. So it makes this and a new carbon-carbon double bond. So that's the ultimate goal of this reaction, is to form a carbon-carbon double bond. That is a Wittig reaction. So here, in this question, on your Wittig reaction question, you can eliminate anything that doesn't make a carbon-carbon double bond. So this has a carbon-carbon double bond. This does too. This one does not. It has one here, but also has this one. This doesn't have a carbon-carbon double bond, and this doesn't have a carbon-carbon double bond. So we're left with C, which these are hard to visualize, D, and E. Sometimes I'll just outline the ones because, this looked like C was talking about that structure. So now we're just trying to see, we've eliminated it down to 3. Which one of these has what we want? Well, there's no carbonyls left, so it can't be that one. So it's D or E. So on the carbon-carbon double bond, one side needs to have a hydrogen and a benzene, and the other side needs to have a methyl and a benzene. So that should be your right answer, should be answer choice E. The one that was missing here is this should have been CH3 and then the benzene. So answer choice E should be your right answer. Okay. 17 is another Wittig reaction, so you'll be able to see it a little bit better. So this attacks and kicks out. So now you have CH3 with a bond to phosphorus. I'm just going to draw these as R groups because it's easier to visualize. That's positive. Then your NaH, the H minus, is going to take one of these and make a double bond. Okay, so that gets you CH2 double bonded to P with all these R groups. So those are the first 2 steps. This can have the alternate form as the Ylid, where this is a lone pair and this is a positive charge. You don't have to draw it that way for the purposes of solving a practice problem. I would just stop here. And then you line up what you're going to mix it with. You've got a benzene ring over here and a CH3 group over here. So first this happens. And I always draw my box out. PR3, there's 3 R groups. This is a C with 2 H's. This is a C with a benzene and a CH3, and this is an oxygen. Then it happens again, and you end up with CH2 double bonded to C with a benzene ring and a CH3, and then this P, R, 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 double bonded to oxygen. Once you get faster at this, you can line these up and then just know that there will be a double bond here. And that's faster. But if that's confusing to you, if what I just said is confusing to you, just go step by step for each of these reactions. Okay, so which is the right answer here? Let's see. This actually, answer choice A looks promising. It's got a benzene ring and a CH3 and a CH2 on the other side. This looks crazy. There's no carbon-carbon double bond. This has a carbon-carbon double bond, but it only has, let's see. Oh, it doesn't have a CH2 on this side. This should be CH2 and this should be CH3. So that's why that one's wrong. This doesn't have a carbon-carbon double bond, and this one has 2 benzene rings and we only have 1. So answer choice A is your right answer. And you could have eliminated straight off the bat B and D because they didn't have carbon-carbon double bonds, and that's the whole point of a Wittig. So if you see a phosphorus with 3 things around it, an alkyl halide, phosphorus with 3 things around it, an alkyl halide, a base, and a carbonyl carbon, that's a Wittig reaction. And the Wittig reaction is always going to give you a carbon-carbon double bond. And this is another one. So in this case, they're giving you the final answer, and they're asking what would you have had to have as your missing piece. So we have the phosphorus with 3 things around it. We have a base, and we have a carbonyl carbon. So we're missing an alkyl halide. So whatever is missing is an alkyl halide. We also know if we line our stuff up right, we should have our C double bond oxygen with these crazy wings on one side, and then P with something right here. And the thing it looks like is there is this. Then the box reaction would happen twice, and you'd end up with this. And that is what we end up with. So what do you need to get to this? Well, the phosphorus attacks P with 3 things around it, a halide to form that bond. It does a substitution reaction. So, first it's protonated. So if we had the proton added back in, it would be like this. P plus with 3 R's and a hydrogen. And the step before that is the phosphorus does a substitution, or an SN2 reaction with some kind of alkyl halide. So the PR3 attacks and kicks that out to get this structure. So the right answer is going to be cyclopentanone. That's tempting, but that's not the right answer because you already have your carbon-oxygen double bond there. And to help you, you should be able to know what a cyclopentanone is. Cyclopentene doesn't have an alkyl halide. Cyclopentanol, also not an alkyl halide. Oh my gosh, I didn't even realize. If you just knew the thing you were missing was an alkyl halide, you could narrow it down that way and not even have to do all of this reverse reaction. You need an alkyl halide so that the phosphorus can attack. Okay, and very last question, number 19. Ooh, this looks like a fun one. Okay. So first, we have a conversion of a carboxylic acid into a chlorine plus benzene and Lewis acid for Delcraft's acylation. I always flip this around because it's just easier for me to see. So this is going to attach right here. 1, 2, 3. 1, 2, 3, and the third has 2 methyl groups on it. Okay. And, the next step is the rainy nickel. Sulfur and rainy nickel. So this is going to attack and kick up. I'm drawing the mechanism just so you can see it. I don't know that you'll be tested over it, but I think it's always beneficial to know the mechanism. So then it looks something like this. I imagine that first this protonation happens and you get an alcohol, and then this protonation happens and you get a good leaving group, OH2 plus. So then you have your sulfur and an S minus over here, and then your R group. Then this would attack and this would leave, although it might do it where the leaving group leaves first, depending. And that's how you end up with this group. So I told you I don't think you need to know that for this class, but it's easier if you do. So I always like to have the mechanism, and then this just would get deleted. So you'd end up with 1, 2, 3, a 3 carbon chain, 1, 2, 3 with 2 methyls at the end. So your right answer is answer choice E. Answer choice 1 is wrong because it stops after step 2. B is wrong because all kinds of crazy. The chlorine would add at the other side, the acyl chloride, so that's not right. C is close. Instead of the rainy nickel completely eliminating that group, it turned it into an alcohol, and that's not right, but I could see why that's what some people would think. And then this has the methyl group in the wrong place. It would be down there for it to be right. That's how you get answer choice E. I hope this was helpful for you guys for chapter 16. Let me know if you have any questions or if you need any help, and good luck on your exam.